Hello guys and welcome to my YouTube channel. Today we're going to be solving the February-March 2021 question paper 424 physics, and the question paper is 2 hours long, and we're going to go in depth explaining how some of the questions were supposed to be worked out. Please do subscribe to the channel so that you can be able to get more content like this and you can be able to understand physics. So let's get to it. We've got a long paper ahead of us. Okay, to start off, we're starting off with a recall question. State Newton's law of gravitation. Okay, so say Isaac Newton discovered this law, and it's called the law of gravitation. Basically, it states that the gravitational force is directly proportional to the product of the point masses and inversely proportional to the square of their separation. What am I even saying? Well, if you have two masses, mass A and mass B, these can be planets. The force that these planets exert on each other will be equal to the product of their masses. So they're going to have different masses, and there's going to be a separation between them. And the square of that separation is going to, and the product of their masses divided by the square of the separation is going to be the law of gravitation. Newton was a very, very smart guy. We should give them that. For question B, we've been told that planets have been observed orbiting a star in another solar system. Now, our solar system is the Milky Way galaxy, but this is another solar system. We don't even know where it is. But basically, measurements are being made of the orbital radius r, right? So we're making measurements of the orbital radius r and the time period t of each of these planets. So we have time period t, and then we have orbital radius r. What does this even mean? It means that you have a planet that is orbiting the center of a star. So you have multiple planets. For example, you can have 3 planets. Let's just have an example, 3 planets. In this case, we're going to have multiple planets, right? They're going to orbit with a specific radius, and it's going to take a specific time for them to complete an orbit. That's an orbit, right? So when they did that, they then found this graph that relates the radius of the orbits to the period itself, right? And they got that little graph, which is very, very nice. And what they're asking us is they've given us the relationship between t and r. From that graph, they've given us the relationship between the period and the radius. T squared is equals to 4 pi squared r cubed divided by gm, where g is the gravitational constant and m is the mass of the star. What do they want us to do? Okay, so what they want us to do is to determine the mass m that is present. Where are we even going to start? Okay, now if you look at this, this is the m that we want to find. But then we can sort of make something out of this, right? If you look at this formula, right, it's saying t squared is going to be equal to 4 pi squared, okay, 4 pi squared divided by g multiplied by m, all of that r cubed. Okay, so we have a relationship between t squared and r, right? T squared is going to be equal to that specific relationship. And as you can see, this is an equation of y. This is on our y-axis is equal to m, and this is the value of x. Y is equal to mx plus c. In this case, the plus c is actually 0. So what this implies is that the gradient of our graph, okay, the gradient of our graph is going to be equivalent to 4 pi squared divided by g multiplied by m. Right? The gradient of our graph is going to be 4 pi squared divided by g multiplied by m. So if we want to find the gradient, what are we going to do? If you want to find the gradient, what you're basically going to do is going to take change in y over change in x. But in this case, we want to find the mass. So we make the mass the Sabito formula. Our mass is going to be equal to 4 pi squared, okay, divided by g multiplied by our gradient. Okay, so if you want to find our mass, we're going to have 4 pi squared, all of that divided by 6.67 times 10 to the power of negative 11 times. Now we want to find our gradient, right? But if you look at this specific graph, right, if you want to find the gradient, to find the gradient, basically you need a point. Okay, so in this case, if I'm looking at this accurately, right, I have this specific point which is over here that I could take, right? I have this specific point that I could take, and if you look here on the x-axis, if you look here, we have 0.4. right, on this specific case. Then if you look on this other side, we have 0.8. So those are the two values that we're going to deal with, 0.8 and 0.4, and we're going to use those values to sort of find our gradient. So if you go back, if we're looking at this, our gradient is going to be our change in m. So in this specific scenario, our gradient is basically going to be our change in the y value. Like I've said, we have 0.8, but remember, it's saying year squared, right? Year squared. So we're trying to convert that year so that it goes to days, right? It's much easier for us to work with years converted to days, converted to hours, converted to minutes, so that we end up with our years in seconds, which is the conventional unit that we're going to deal with. So if we put it over here, right, our change in y, we're going to have 0.8, like I've said, right? But then this is just 0.8 years, right? So we're going to have 3,600 multiplied by 365. That's 60 minutes times 60 seconds, right? Multiplied by 365, multiplied by 24, all of that squared, okay? Because it's years squared, divided by 0.4, multiplied by 10 to the power of 34. So this is the calculation that we're putting here, right? We just have 0.8, right? This is sort of the calculation that we're dealing with, right? And if you punch it all in the calculator, I'm not going to encourage that, right? What I would encourage is for you to break down the calculations into different things. But then if you want to do that, it's perfectly fine. But then I would really encourage you to break it down into multiple calculation. And if you punch that in the calculator, what you're going to get is you're going to get a mass of 3.0 times 10 to the power of 30 kgs. This is going to be your mass, 3.0 times 10 to the power of 30 kgs. Very important for you to be thinking of that. Moving on. A rock of mass m is also in orbit around the star. Now we have a little rock that is now in orbit around the star. So very important key points that you're supposed to be noting. We have a rock of mass m that is in orbit around that specific star. Right. So the radius of that orbit is going to be r. The radius of the orbit of that ball is going to be r. And what do we need to do? What I want to do is explain why the gravitational potential energy of the rock is negative. I'm going to tell you something that is going to be a little bit tricky to understand, but I hope you get it, right? If you have two objects that are closer together, right? If you have two objects that are closer together, and if you let them go, right, because of their masses, remember we said that gravitational forces are attractive. Because of their masses, they're going to come together, right? Because they're going to attract each other. Gravitational forces, like we've said, are attractive. The reason why when you jump high, you fall down is because the earth is attracting you, okay? Now, let's try to do that much more. Let's try to separate these two masses, right? Even occurs in magnets. If you put magnets far apart and if you try to bring them together, you reach a point where it's not even going to occur. That's the same thing that happens with gravitational potential energy itself, right? If masses are closer to each other, implying that they're just going to come closer. They have a higher potential to come closer together. But if you separate them away from when they're so far away that they're at infinity, they're not going to come together. So that means the potential is zero. The potential for them to come together is zero. Right? The energy that they possess due to being in a gravitational field is going to be zero because they're so far away. But if you bring them closer together, they're going to attract. So if you're far away and it's zero, when you bring them together, it's going to be negative everywhere else, right? Because it's going to be zero at infinity. It's going to be negative everywhere else. And negative, remember, implying that these forces are attractive, right? It could have been positive if they were just repelling or something like that. But it's going to be attractive, meaning it's going to be negative. Another way you can think of this, like the third point. So the first point is stating that at infinity, gravitational potential energy is zero. The second point is stating that gravitational forces themselves are attractive by nature. The third point, you can state that work must be done to move the rock to infinity. What do I mean by this? Now, if you're going to take a rock, right, and if you're going to place it at some point and leave it, it's going to fall, right, on its own naturally. That's weird. That never happens. If you leave, let's say if you have a box and you put it on a surface, you're going to have to apply a force to move that box. It's never going to move on its own, right? So it's only when it moves on its own that we call it negative work, right? Because other than that, how does it make sense to say that, you know, the box is just going to move on its own, right? It's not going to make sense. So it implies that work must be done in order for us to move the rock to infinity. We're opposing the gravitational force. But if you don't, and if you let it go, it's just going to move on its own, right? It's not even going to do work. It will just be relaxing, minding its own business, and just falling down due to the nature of the gravitational force itself, right? And that's very weird. The rock itself is not doing work. In other words, it's doing negative work, right? Work is being done on the body itself, right? So you can think of it as you're not eating, but stuff is actually, you know, coming out of you. Water is coming out of you, right? That's negative work, right? But positive work is you eating. Negative work is something coming out of you. So that's the same thing that's happening with the rock. The rock is sort of being driven away from infinity. So it's sort of doing negative work, right? And in order for you to do that, to go to infinity, you're supposed to do work. So that means you're gaining potential, right? And it can't be positive everywhere else. If you're gaining potential by doing work to move to infinity, you can't have a high positive value, right? I hope you get it. So because it can't be positive, right? If you're doing work, it can't be very positive everywhere else because it has to reach zero, right? So the only logical explanation is for gravitational potential energy to be negative, right? So it's a little bit of a long explanation, but what you just need to know is potential at infinity is zero. Why? Because everywhere else you have to do work to actually get to infinity. You have to do work to overcome a gravitational force. But if you already have a positive gravitational force of 1,000,000, why do you even need to do work, right? You have to sort of lose work. But in this case, we gain work. So that implies that the gravitational potential energy itself has to be negative everywhere else. I hope it makes sense. If you have any questions, please do comment in the comment section below. If you want a separate video on this concept alone, please be free to say so, and I will be happy to help. I'll move on to the next question. Show that the kinetic energy of the rock is given by EK is equal to GMM over 2R. What you're going to realize is that if a rock is orbiting, it's going to need a centripetal force, right? This is an orbit. You've done centripetal forces, and you know you're going to need a centripetal force, right? And that centripetal force is provided, guess what? By the force of gravity, right? The rock wants to fall towards the planet. So the force of gravity is sort of going to provide the centripetal force. So I'm going to write a little equation here. The force of gravity is GMM divided by R squared. That's going to be, remember the centripetal force, mv squared divided by R. Right, you multiply by R, you multiply by R over there, you end up with V squared, right? If you look at that, is going to be equal to GM divided by R. But what do we know about kinetic energy, right? Kinetic energy sort of describes the energy due to motion. If you're just moving, you're gonna have some kinetic energy. So we know that's half m multiplied by V squared. So our V squared is GM, so it's GM over 2 multiplied by R, and then that little m is going to pop up there, right? So you're going to get your 2 marks. That's a short question. Another formula, using the expression in C part 2, derive an expression for the total energy of the rock. Okay, so you're going to think about this question and say, they want me to determine the total energy of the rock. How much energy does it have? Remember, number 1, it has gravitational potential energy. Number 2, it has kinetic energy. So we have 2 specific things, right? So total energy, right? Your total energy is going to be the sum of your kinetic energy plus your gravitational potential energy. Your kinetic energy, we have it, GMM divided by 2R. But then your potential energy, however, is a little bit tricky, right? Because if you think of it, potential energy is sort of described as gravitational potential multiplied by m, right? So gravitational potential is defined as the work done to move a unit mass from one point to infinity, right? What work are you going to do to move one mass from a certain point towards infinity, right? So the work done itself is the gravitational potential energy. So it's going to be equal to phi multiplied by m. But according to calculation, if you're very interested, there's going to be separate videos on this specific concept alone. But then phi itself is known as GMM over R. So we're going to have GM, right? GMM over R, because phi is GM over R, right? So GMM over R is going to be phi times m. And we're going to put a little negative. Remember, we said gravitational potential energy is negative, right? Why did they ask you if gravitational potential energy is negative? Because you're going to have to put it over there, right? And remember, we explained why it's going to be negative. So if we go here, it's going to be plus negative GMM divided by R. If we're doing a little math here, this is sort of 1/2, right? Minus 1/2, why not? Minus 1 as a whole, right? So we're going to end up with minus GMM divided by 2R. Right, so we have to think, what is gravitational potential energy? And this is in your textbook, guys. This is gravitational potential multiplied by the mass. And you're going to put a negative because gravitational potential is negative, right? You're going to have to gain gravitational potential as you move far and far away. So it's supposed to be negative so that you gain it and it becomes zero wherever you are trying to go. Okay, move on to question number 2. A fixed mass of an ideal gas, or of a gas, right? An ideal gas is at a temperature of 21 degrees, right? And the pressure of the gas itself is 2.3 times 10 to the power of 5 pascals, and its volume is 3.5 times 10 to the power of negative 3 pascals. Calculate the number n of the molecules in the gas. So we know that PV is equals to n RT, okay, where P is the pressure, right? And V is sort of the volume. Okay, P is the pressure, V is the volume, N is the number of moles, R is the molar gas constant, and T is going to be your temperature. And what we want to do is find the value of N, right? So N being the number of particles. So how we're going to do that is this equation is going to help us find the number of moles, right? And the number of moles, if you're wondering where is this equation even coming from, don't worry, I got you, right? So we know that pressure is directly proportional to temperature, right? The higher the temperature, the greater the pressure, right? Pressure and temperature are very related, and pressure is inversely proportional to volume, right? And this makes sense. A bigger volume means there's going to be lesser pressure, right? A very small volume means it's going to be higher pressure because the molecules will be bumping and bumping across the walls of the container. So it means in total, pressure will be directly proportional to temperature divided by V. So PV directly proportional to T, and then you introduce a constant, PV will be equal to KT, and our constant in this case is NR, right? Number of moles is a constant because it's the gas that you're talking of. Then R is just another constant that you're given in the data booklet. I think if you look over here, this is your value of R, right? 8.31, right? Use your data booklet, guys. But okay, so if you want to find the number of moles, what I'm going to do is the number of moles is going to be our pressure, which is 2.3 times 10 to the power of 5 multiplied by our volume, which is 3.5 times 10 to the power of negative 3, right? And we're going to divide by the value of R, which is 8.31, right? And then we're going to multiply by, okay, we're going to multiply by the temperature. Remember to convert it to kelvins, otherwise you're going to upset Lord Kelvin, right? Okay, so we have 21 plus 273. Always convert it to kelvins, guys. Okay, so our number of moles in this case is going to be 0.329, right? And what do you know? You have number of moles and you want to find the number of molecules. Very important formula you're going to need to know. Number of moles is equals to number of molecules divided by 6.02 times 10 to the power of 23. This is Avogadro's constant in honor of Avogadro, right? These guys were smart. I tell you that. The number of molecules is going to be 0.329 multiplied by 6.02 times 10 to the power of 23. You do the math and you end up with 2.0 times 10 to the power of 23 molecules. 2.0 times 10 to the power of 23 molecules. Okay, the mass of one molecule of the gas is 40 U. Determine the root mean square RMS speed of the gas molecules, right? We want to determine the root mean square speed of the gas molecules. What are we going to do? Okay, let's think about this, guys, for a little bit, right? What is the formula that we're going to use? We have this specific formula, which is over here. P is equals to 1/3 Nm over V squared, right? 1/3 Nm over V squared. Very important formula that you're going to need to remember. Okay, PV is going to be equal to 1/3 Nm multiplied by C squared. Right, so this is the formula that we're going to be using for this calculation. But you know me, guys, I just don't like using formulas without knowing where they're coming from. So I'm going to do a little math on the side. If you don't like this, please just skip forward. All you need is to know this formula and, and move on with your life, to be honest. There are a lot of things you need to do. But if you're very interested in understanding where this formula comes from, I want you to take your eyes on this specific side. I'm going to explain to you some little physics, right? Okay, so imagine you have a little particle over here, right? A little particle minding its own business, right? Moving, and we're going to assume that it's going to move in one direction. But remember, velocity is pretty complicated, right? It could be moving at a, direction like so, right? The velocity should be like this, right? But then we resolve it into components, right? We resolve it into multiple different components these components can be component in the y, right? It can be a component in the x. It can be a component in the z. Remember, this is a 3D thing, right? 3D means it can move in the x, move in the y, move in the z, right? I want you to grasp that concept. Okay. So what you're going to do is that if you want to find that little velocity v over here, right, it's going to be the summation of, right, it's going to be the summation of your vx, right, over here. So it's vx squared is going to be equal to vy squared. It's going to be equal to z squared. Remember, we are assuming that these components are equal, right? Because they sort of model it as a cubic container, right? They sort of model a particle as a cubic container. Why? I guess it's to make calculations easier, right? So that it's a little bit much easier for you to be able to think of that. So if you model it, it's going to have multiple different directions, and to find the mean, we sort of assume that the components itself are going to be equal. We assume, guys, physics is full of assumptions, but what I want you to get is that the velocity in the x, right, itself will just be 1/3 of the velocity, of the total velocity that is going to be present, right? Because you have three components, right? The velocity itself is made up of three components: the x, the y, the z. And we said those three components are all equal, so it means that the velocity in the x will just be 1/3 of the velocity in the y. I hope I'm not confusing you. Okay, so we want to find the relationship that I've been talking about here. Let's look at this scenario, right? You have a little cube, right, which is over here. You have a little cube, which is over here, right? What's going to happen is you have your particle, okay? Your particle is going to move about its day with a certain velocity in the x, okay? Move about its day. It's going to hit a wall, right? And then it's going to come back, right? It's going to hit a wall and it's going to come back. Remember, we've assumed that it's a cube, which is L. The container that was sort of doing that, because we're considering a gas particle inside a cube of length L, right? So that we can be able to make our calculations easier. Okay. So it is, as it moves, it's going to hit here. It's moving, remember, the velocity Vx, right? And it's going to move here and it hits the hole. And there's going to be a change in momentum, right? There's going to be a change in momentum, because if this was direction and the momentum mvx, right, it's going to move now in this direction, and the momentum is going to be mvx, again in the negative direction, right? We assume no energy has been lost. So with the cube, we assume a gas particle is trapped inside a cube. We want to find the relationship between the pressure, the volume, and the speed of that particle. So what's going to happen is you're going to have pressure, right? You're going to have pressure which is equal to force. Pressure is the force per unit area, okay? But remember, what is a force? A force is the rate of change of momentum divided by time. The rate of change of momentum divided by time. So the area is just going to go down on that little bottom. But remember, we said that the change in momentum, it went like this, Vx, then it went like that back, right? So it means that final momentum, which is negative mvx, minus initial momentum, which is negative mvx, right? We get negative 2mvx. So it means our change, the magnitude of the change, is going to be 2m, the velocity in the x, divided by, okay, our area, right? If you look at this, our area, we want to find our area. It's sort of a length, right? Remember we said it's a square, it's a cube, sorry. So we're going to have L squared, right? Sort of our area over there. Then our time, remember, velocity is going to be the distance that it has traveled. So for this momentum change to occur, right, it's going to travel a distance of L, then it comes back a distance of L for that momentum change to occur. So the total distance that has been traveled, guess what? It's 2L, okay? And the velocity itself is Vx, right? Okay. And then we're going to have L cubed at the bottom here, right? We're going to have L cubed divided by 2, okay, sorry, multiplied by 2 divided by Vx at the bottom here, right? Substituting this specific thing. Okay, so end up with pressure is going to be equal to 2m, velocity in the x divided by, but L cubed, remember, for a cube is the volume, okay? The volume divided by, so 2v divided by Vx, right? These two things cancel out. So we just have 2v divided by that specific thing. And then our Vx is going to flip and go to the top, right? Find time for it. So we're going to have m Vx squared, okay, divided by v, right? And if you put it on one side, we're going to have p is equal to m Vx squared multiplied by p. Pv is equals to m Vx squared. But remember, we said that Vx is actually 1/3 of the total velocity itself, right? So it means PV is going to be 1/3, right, of m, just the velocity of itself squared, okay? And we're going to now end up with PV, but this is for one particle. For many particles, we're going to have 1/3 of n. If it's for one particle, for many particles, just multiply by n, right? So if you multiply by n and you multiply by m, you multiply by v squared, that's going to be the relationship that you have over here. PV is equal to 1/3 nmc squared. It's a little bit of a complication, but it has been asked before. So I'd really encourage that you just know that, right? We have 3 directions. Those directions are equal in magnitude. It's an assumption that we make. Physics full of assumptions, right? They could be different, but to little extents. Then we say in one direction, it's 1/3 of the total velocity, okay? If a particle hits that wall, it's going to change its momentum. We assume it's elastic. So the total change in momentum is going to be 2mvx, right? But pressure is force per unit area. And force, rate of change of momentum, delta p, that time goes down. And the time is the time taken to go from that and come back for that momentum change to occur. The distance is going to be 2L. And we're going to multiply that divided by our velocity, which is Vx, right? We have L squared, that gives us L cubed. Our velocity, we arrive to Vx, having being 1/3 of the total velocity squared, and we end up with our specific equation, right? If you didn't get anything, please do ask, right? I can make a separate video again, just comment it, but it's important for you to understand it's gonna be examined, right? If you don't know it, just use the formula, right? If you don't want, just use the formula. So in this case, we want to find the root mean square speed of the gas molecules themselves. So the value of C is going to be 3 PV divided by N multiplied by M, the square root of all of that, right? So the square root of all of that is going to be the value of C. And if you're looking at that, it's the square root of, right? It's the square root of 3 multiplied by 2.3 times 10 to the power of 5 times 3.5 times 10 to the power of -3, right? That's the pressure and the volume. All of that divided by, okay, our N is 2.0 times 10 to the power of 23. Our mass is 40, right? You have 40U. Remember the atomic mass, 1.66 atomic mass unit times 10 to the power of -27. In total, that's going to give you 426.44. You round that off, you get 430. 430, right? Very important for you to be thinking of that. The temperature of the gas is increased. We're going to increase the temperature, right? Heat it up so that it goes to 84 degrees. So they want to find the ratio of the new RMS speed of the molecules over the original RMS speed of the molecules. But remember, guys, I know a little ratio, right? I love ratios, right? Just know a formula, plug it in, and you get a relationship. I know that PV is equals to, like I've said, 1/3 N M C squared, right? But I also know PV is equals to nRT, right? I'm a little sneaky. So I can put it over there, and I have nRT being equal to 1/3 NMC squared. Look at this. N is constant. M is constant, right? I have a lot of constants here. N is constant, M is constant, R is constant, N is constant. So I have a relationship between my value of T being directly proportional to my value of C squared. Isn't that cool? So it means that C is directly proportional to the square root of the temperature, right? Sort of a relationship that I thought of here. So it means that the square root of the new temperature divided by the square root of the old temperature is going to be the ratio itself. So if you have this scenario, it's the square root of the new temperature. Remember, it was increased by 84, right? If you were drinking 2 cups of water and you increase by 2 cups, how many cups are you drinking? 4 cups. So if you had 21 degrees Celsius, right, and you increased by 84, what is your new temperature? It's not 84, guys. It's 21 plus 84, right? So you have 84 plus 21. But remember, this is in degrees Celsius. You want to convert it to kelvins, right? Remember, do not upset Lord Kelvin, right? He's gonna, he's gonna kill you if you just don't put him over there. Okay. And then on the denominator, we have the old temperature, which was 21 plus 273, right? Punch that all in your calculator and you get 1.1. Okay. Move on to the next question. Using a simple kinetic model of matter, describe the structure of a solid. We want to describe the structure of a solid. So you sitting here, wherever you are watching my video, you are solid, right? Everything you're looking around you is a solid. And you've just been asked, describe the structure. But in life, we never really take time to get into the finer details. So, that's why we're here. So what are we going to do, right? Remember, it says using a simple, right, kinetic model of matter. So let's describe the structure. So one of the things that we're going to say is that the particles, okay, the particles, this can be particles, this can be atoms, okay, this can be molecules, right, are close together. Okay, very important for you to be thinking of that. The particles, molecules, or atoms are closer together. Right? Then another point is that they vibrate about a fixed position. Okay? They vibrate about a fixed position. They just shake a little bit, right? But you can't feel it, right? Your eye is solid. It's not like you're just shaking unless you're cold, right? It's winter here, but unless you're cold, you're just going to vibrate about a fixed position at a very small level that you can't even feel it. Okay? Vibrate about a fixed point. Then the last point, a little bit, if you want to go deep down into the nitty-gritties, is just say that it's in a regular pattern, right? They vibrate in a regular pattern. So if you're asked to describe yourself, right, describe a solid, the particles vibrate about a fixed position. Fixed position, they just shake a little bit, right? And it's in a regular pattern as it's going to occur, right? The particles and atoms are very, very close together. If it wasn't, you're going to be air, right? Imagine having your lung on that side. It's going to be a mess, right? So that's what we need to think. Specific latent heat of vaporization. What does this even mean, right? Remember, you have a lot of stuff that you've learned, but I'm going to ask you guys to be very particular when you are reading to remember every single thing, right? Latent heat of vaporization, and they give you a little help here, right? They said vapor means gas, so is the energy required to convert 1 kg of liquid so that it goes into gas without any change in temperature. That's latent heat of vaporization. Latent heat of fusion is the amount of energy required to change a solid to a liquid, right? You want to change a solid to a liquid without any change in temperature. So the amount of energy you need to change a liquid to a gas is far much greater than the one that you're going to need to change a solid to a liquid. And they're asking why. Why is that occurring? Well, if you think about it, there is a greater spacing in the molecules for vaporization, right? There's a greater increase in spacing. Okay? There's a greater increase in spacing of molecules for vaporization as compared to fusion. Okay, so there's a greater increase in spacing for molecules for vaporization, okay, as compared to fusion, right? Remember, for vaporization, we have to break away the forces completely. But the same thing is not going to happen for fusion, right? For fusion, we just want to weaken them so that there's a liquid. But with gas, break them completely. So you're going to have an increase in the spacing that's going to affect the amount of energy that you're going to need. So for vaporization, we need a lot of energy. But for fusion, we don't need that much energy like that. Okay. Move on to the next question. A heater, right? We have a little heater that's supplying heat energy at a constant rate to 0.045 kgs of a substance. We have a substance, a heater, and the heater is heating the substance. Okay. The variation with temperature of the substance is shown. The substance is perfectly insulated from its surroundings, right? And this graph is sort of describing the changes that are occurring, right? Let's think about this. Okay, so determine the temperature at which the substance melt, right? Was probably a little solid, then turning into a little liquid, and want to determine the temperature at which the substance melts. You have this graph. This graph refers to the changes in temperature during a variety of processes. Guys, I want you to lock in. You can't have a change in temperature during a change of state. By heating, you're applying energy. Okay, now the energy goes to two things. It either increases the kinetic energy. Temperature refers to the kinetic energy, so atoms will just be vibrating a little bit more, right? Or it's going to separate the molecules. It's going to move them far apart, right? And it's going to cause the state to change. So there are two things that's happening, right? So in order for you to change state, you have to break away the forces, and you need energy to do that, right? You can't vibrate and break away at the same time. So the energy is going to be devoted to moving the molecules away and not necessarily increasing the temperature. So whenever there is a constant temperature, like at this point, it implies a change of state. Okay, and at this point it implies a change of state. And you're going to ask me, what is this change of state and what is that change of state? Guys, okay, you're in A levels, right? And you only do two changes of states, unless you've done something else. But I know it's solid to liquid and liquid to gas. Out of those two, the first one has to be solid to liquid, right? And then the second one has to be liquid to gas. It can't be the other way around. And you can't have, another state. You could ask me, what if this is liquid to gas? But then this would be what, right? This would be what, guys, right? So this is liquid to gas, right? Then we have a gas increasing in temperature. The gas is now shaking. This is solid to liquid. Then the liquid is now shaking and shaking and shaking and shaking and shaking, shaking. Then it separates, right? So that is sort of what we're trying to see over here. So determine the temperature at which the substance melts. That's going to be negative 100 degrees Celsius, right? Negative 100 degrees Celsius. Very important for you to be thinking of that. The power of the heater is 150 watts. Using data from Fig 3.1, calculate in kilojoules per kg. Pay very specific attention to units. The specific latent heat of vaporization of the substance. How do you find specific latent heat? Well, one of the things that we know is that the specific latent heat of fusion is the amount of energy that will be supplied divided by the mass, right? I use Q for energy. You can use E, right? We just want to, make it clear. So Q is going to be equal to M times the latent heat of fusion, right? How much energy have you supplied per unit mass of a substance? Sort of like the latent heat of fusion. And that energy is just going to break away the forces, right? To change that state from liquid to gas. So the energy that will be supplied, remember you have power. Okay, you have power that is over here, and you want to find latent heat of vaporization, guys. It's the second change. The first change was fusion. The second change is vaporization. Okay, so in order for you to get energy, power is the energy transferred per unit time. So your energy is going to be your power multiplied by your time, right? That's going to be equal to your mass multiplied by your latent heat of vaporization. Let's think about that. So our power is 150 watts. And what is our time? Let's go on our little graph. We're starting here. It's 3 over here. And then here we have 8, 8.2, 8.4, 8.5. Okay, so we have 8.5 minutes. And then we have 3 minutes on that side. So we're going to have multiplied by 8.5 minus 3.0, right? Multiplied by 60. 60 being our time, 60 seconds, right? Guys. And that's going to be equal to our mass 0.045, right? 0.045 multiplied by L. So the value of L is just going to be equal to 8.5 minus 3.0 multiplied by 60 multiplied by 150 divided by 0.045. So the value of L, what is going to be? It's going to be 1100 0.030 zeros divided by 1,000. You're going to be ending up with 1,100 kilojoules per mole, right? 1,100 kilojoules per mole. Suggest what can be deduced from the fact that the section Q on the graph is less steep than section P. Okay, that's a little sneaky. You could lose this mark if you're not careful, right? It's a bit tricky. Okay, why is section P, right? Why is section Q less steep than section P? Let's think about this. Okay, so section Q is relating to how much the temperature is changing, right? So let's try to analyze steepness. When I see the word steepness, I think of gradient, right? So the gradient in this case, right, is going to be the change in temperature divided by the change in time. That's my gradient, right? Telling me how much the temperature is changing per unit time. So if it's very, very steep, it means that we have a higher change in temperature, right, in a short time. Okay? Oh, this is for it being steeper, right? But if it's less steep, right, if it's less steep, okay, this is just for steep, but if it's less steep, let's look at that. If it's less steep, what we're going to see is that we're going to have a lower delta T, right, over a longer time. Right, so it's going to take longer for a change in temperature, right? So it's what that means is that you need a lot of energy in order for that thing to have an increase in temperature. And what measures the amount of energy you need to cause an increase in temperature? That's going to be the specific heat capacity. Guys, these questions are out of this world, right? We just have to make a lot of connections, right? So gas has a higher, specific heat capacity. If you don't get it, it's a bit tricky, but it's 100 marks, right? You can sort of recover from that, to be honest. Okay, heat capacity, right? Important for you to be thinking of that. Moving on. The definition of simple harmonic motion, very simple, but harmonic motion, not harmonic like music, right? Harmonic as in sort of oscillations, pendulums, acceleration, displacement, opposite directions kind of thing. So if you want to think of this, okay, so we've been asked to state the significance of the minus sign in the equation. So you're going to need to know the definition of simple harmonic motion if you're going to do AS level physics. So what is simple harmonic motion? Sort of defined as the motion of a particle about a fixed point. So there'll be about a fixed point such that the acceleration is proportional to the displacement, right? But they're in opposite directions. What am I saying? If you consider a pendulum, as a pendulum is rotating from side to side to side, so what they're saying is that the acceleration increases as the displacement itself from the equilibrium position is increasing. So the velocity sort of increases or decreases until you reach zero. Right, so the velocity has to reach zero over there. So you're going to have an acceleration that's going to be opposing the displacement, right? But the acceleration will be increasing. And as the displacement is getting smaller, acceleration sort of increasing so that the velocity is maximum at equilibrium. Sort of simple harmonic motion. But then what you're just going to say is that the negative sign tells me that acceleration, okay? Oh, sorry. What's going on? Okay, so it tells me that acceleration, right? Acceleration and displacement, right? And displacement are in opposite directions, right? And that's very important, right? That tells me that, if acceleration is here, displacement is opposing that. Question B. We have a little trolley that is on rest on a bench. Scenarios in physics, they never, leave each other. Two identical stretched springs are attached to the trolley as shown. The other end of each spring is attached to a fixed support here, child support. Okay, let's see. We're given the unstretched length of each spring is 12. So before it was stretched, right? Before initially, before it was even stretched, right? It had a length which was equal to 12 centimeters. And then here we stretched it, now it is 18 centimeters, right? And here we also have 18 centimeters, right? Remember, it's equal, we're at equilibrium, right? Show that the resultant force on the trolley at the moment of release, the moment you release is 0.77, but there are conditions, guys. The trolley has been displaced 4.8 centimeters to one side, right? And then release. So we're sort of touching the trolley and displacing it, but we're displacing it for 4.8 centimeters. That is very, very important because it's going to have several implications. Let's look at it. So if you have a plane like so, right? If you have a little plane like so, and if you've displaced it now to one side, you're going to have a longer thing on this side, and you're going to have a shorter thing on this side. Because by pushing it to one side, what you're doing is you're sort of increasing the extension on one side, but decreasing the extension on the other side, but by the same amount, which is going to be 4.8. So on this side, you're going to increase it 4.8 plus 18. That's going to be 22.8. Okay. On the other side, you had 18 and you're sort of removing 4.8, right? You're pushing it forward and you're sort of compressing that so that it goes from 18 and it goes to 13.2, right? You're doing a little bit of, some fun here, right? So we want to find the resultant force on the trolley at the moment of release, which is going to be 0.77. So if you think about it, really, the force is actually related to kx, right? Hooke's law, right? The force is directly proportional to the extension, provided the elastic limit is not exceeded. A little bit of AS knowledge here. Okay, so if you want to find the force, you're going to need the extension, right? So we have two forces, and we want to find the resultant force at the moment you're about to release. So what's important is for us to find the two forces, and the resultant force is the difference of those forces. So we're going to have force 1, F1, and then we're going to have another force, which is going to be F2 because of that specific thing. Now, if you start with F1, we're going to have, let's say we have F1 minus F2. That's going to be my resultant force. So my R is going to be F1 is K, but my K is essentially just 8. And for the first scenario, my extension is the difference between what I have now, okay, and my initial original length. I want you to remember this, guys. Extension is you had an initial length and you had a little bit of an extension at 18, a lot more extension at 22.8, and what is the extension difference that is over there? So it's going to be 22.8 minus 12, not anything else, minus 12, and that's going to give you 10.8, right? In meters, that's going to be 0.108. Subtracted by the other force is going to be 8, and then you have 13.2. Subtract 12.2, then you multiply that, and you're going to get 0.012. You find the difference, and you're going to get a resultant force of 0.77. Remember, guys, you have a force, and you've moved the trolley forward, right? It's going to cause some extension to decrease, 18 to a smaller one. You have another one, and it's also going to cause the extension to increase. And we just want to find the differences in those two forces produced. So that as you release it, it's going to move, right? If you release a trolley, it's going to move in a specific direction. It's because of that resultant force that's going to determine how it's going to move. Very important for you to be thinking of that. Now, I want to find the maximum acceleration of the trolley. 1 mark, right? Maximum acceleration. We did this in AS and O level, IGSE. That force, the resultant force, is your mass multiplied by your acceleration, right? So your A max, right? Your A max is going to be, and your A mass is going to be the maximum displacement. And in this case, we displace it by 4.8. So it's going to alternate, right? It's going to be 4.8. It moves and moves and moves. It goes to 18 on both sides. It's going to go on the other side. 4.8, 4.8, 4.8, 4.8, 4.8, 4.8, right? So at the maximum, we're going to have that 4.8. So the resultant force itself is going to be 0.77. Our mass is going to be 250 grams converted to kilos, guys. SI units, 0.25. And that's going to give you an answer 3.1 meters. Right, very important. Use your answer in I2 to determine the period of the subsequent oscillations. So we want to determine the period of the subsequent oscillations. What do we know? We know that the acceleration is negative omega squared x. And guys, I didn't think of this, right? I didn't come up with it. You've been given in the question. The initial question literally gave you that formula. Okay? So we want to find omega. Because why am I doing this, right? Always understand in physics. What do you need? You need period. Okay? And to find period, you need omega. Because omega is 2 pi over t. Describes how the period changes, right? Over one period, you've moved an angle of 2 pi. Over a time, which is 1 period. So in order for you to get omega, right, you're going to get a over x, the square root of that, that's going to be your value of omega, right? So in this specific scenario, your omega is going to be, right, we don't really care much about the negative, guys. To be honest, it's just showing different directions, right? One is increasing, one is decreasing. But we just want to find omega. Our acceleration is 3.1. The value of x is, remember, the displacement that you've moved, right? Which is 0.048. Sorry for that. Let me delete that. 0.048. And the value of omega is going to be equivalent to 8.04. Right? That's the value of your angular velocity or speed, or angular frequency, beat me. So angular frequency is much better. I like angular frequency. So t is going to be equal to 2 pi divided by omega. Remember, omega is 2 pi divided by t. So the value of t is going to be 2 pi. Our value of omega, 8.04. That's going to give you an answer of 0.78 seconds, right? So we're going to put it here, 0.78 seconds. The experiment is repeated with an initial displacement of 2.4 centimeters. Okay. Initial displacement of 2.4 centimeters. What do we know? We know that acceleration is equal to negative omega squared x. Okay. And what they've done here, they've been a little cheeky, right? Very smart guys, been a little cheeky. But if you think about it, I want you guys to think about it really. Nothing much has been really changed here, guys. We have halved 2.4, right? From 4.8 to 2.4. So this is halved, okay? But remember what I said initially. The acceleration directly proportional to the extension. You half x, what's going to happen is you're also going to half a. Half x, half a, okay? But if you're going to do that, does your constant change? Does your constant change, right? It's not going to change. X halves, a halves as well. So, but omega here is just chilling. It's like, guys, why am I not changing as well, right? Omega. So sorry, my friend, we left you, right? Omega is not going to change. It's just going to chill. As x is halved, a is halved. But omega doesn't change. But omega affects the period. Remember, we calculated the period using omega. Right? We didn't use anything else. We calculated the period of the oscillation using omega. So if omega didn't change, that means the period didn't change, right? So what do we do? How do we state and explain that? So we just say the resultant force, okay? The resultant force is halved, right? Fair and fine. And the distance is halved as well. Right? The resultant force, the acceleration, is halved. But, right? But omega is not affected, okay? So we're going to have the same t. We didn't affect omega. What we did is we halved the resultant force. I accept. We halved the distance. I accept. But we didn't change omega. So how is t expected to change? It's not going to change. And if you do that, you get your 9 marks, right? Next question. Amplitude modulation of radio waves. If you're doing the syllabus from 2022 going forward to 2024, you don't do this out of your syllabus for modulation. So we're not going to cover that. If it comes in the syllabus, we just go and cover these questions that we've been out of the syllabus. But to be honest, it's not going to help anyone. Most of you watching are doing the syllabus from 2022, right? Going forward. So we're not going to cover that. Moving to question 6a. We've been asked to state a similarity between the gravitational field and the electric field lines around a point charge. Like, remember, I said a mass exerts a gravitational force. If you're watching this with your friend, which I recommend you do, right? Allow your friends to enjoy physics, or you're in a class, you're at home, you're attracted to your family members, right? I don't mean, not that kind of attraction, right? But I mean, an actual attraction by gravitational force. It's just that it's too small. But every point mass has a gravitational field around them. The Earth has a gravitational field around it, right? And then a point charge has what you call an electric field around it. Why? If you place a positive charge, it's going to experience a force. Repulsive or attractive, a force irregardless. So as that is happening, as it's experiencing a force, it implies that it has to also have an electric field. And one of the similarities between these two is that both have radial field lines. Both have field lines that extend upwards. If you have a positive charge, okay, if you have a positive charge like this, the field lines are radial, right? They radiate outwards like so, okay? And if you have a point mass, right, the field lines are inwards also like so. So one of the things that makes them common is that they're both radial, and that's very, very important. So both have radial field lines. Okay. Move on to the next question. The variation with radius r of the electric field E due to an isolated charged sphere. So I'm going to give you guys a little sphere to play with, right? So the little sphere is charged, right? What does it mean charged? Right? It has a specific charge. It's a conductor. So how do you do that? How do you charge a sphere? Right? So before you even understand this graph, we first just need to understand how you even charge a sphere. Okay? If you have a sphere, you can earth it, right? You can earth a sphere. You're going to have a sphere, as you can see over there on the screen. You sort of earth it like so, right? And you drag electrons away from it. Your sphere is going to be positively charged. But how he does that, you know, I love physics because things are fair, right? Charge is going to be distributed evenly around the surface of the sphere. No one is selfish, right? You don't see, you know, the charges accumulating on one side. They're like this, right? You don't see them doing that and then they leave all of this alone. Or you don't see them, you know, on one side like so, on one. They're evenly distributed around the surface like so, right? And that's pretty fair. I appreciate that, right? And then this creates an electric field that is outwards like so. Such that if you put an electron over here, it's going to be attracted, right? If you put a proton, something positive here is going to be repelled, right? And that makes sense, right? Something positive is going to be repelled, something negative is going to be attracted. But guys, no matter where you are, you're always going to be repelled. It's a conductor. If you approach it from this angle, you're still going to be repelled. If you approach it from this angle, you're still going to be repelled. Now, what that tells you is that the electric field strength is uniform, right? From any point that you are, it's going to be the same. That's very important for us to discover. So as r is the separation, as r being this distance, as you're getting away from the center of the sphere, which is over here, r is going to be this specific distance as you're getting away from the center of the sphere, right? And as r is increasing, we have a variation for the electric field, right? We have a variation for E. And where is this variation coming from? Well, if you think about it, the electric field strength is basically the force experienced per unit charge. And according to, say, Coulomb, the defined charge as KQ divided by R squared divided by Q. These two guys cancel out. So our E is just going to be equal to KQ divided by R squared. So this is sort of like a proportionality curve, sort of. And so it's going to be sort of like a curve like this, like E is directly proportional to 1 over R. Right, sort of like that, but squared just means squared, right? So it's going to be following that same similar shape. But what I'm interested about, that's so interesting, is here. I like this part, and this shows how so much fair, you know, life is. I like this part so much. This is the radius of the sphere, and I'm going to explain why, right? Because we're going to be asked. The next question is state the radius of the sphere, right? The E is 0 inside a sphere. Why is that? There is no field inside a sphere. Okay, so I'm going to put my little sphere over here. Excuse my drawing. A little bit bad, I know. Okay, I can do better than this. Come on. Let me work with computer. Okay. Okay, let's. Okay. Okay, good enough. Right. So, like I've said, the charge is distributed on the surface of the sphere like this, and it does so fairly. Right, so the whole surface is positively charged. All the electrons have been repelled. If we were to take a proton and put it in the middle, or let's say an electron and put it in the middle, it's going to be ridiculous, right? You know, it's like taking a little bun and putting it where people are hungry, taking food and putting it when everyone is hungry. Everyone will sort of be fighting, and no one will actually eat the bun because they're all just fighting with each other. That's the same thing that happens here, right? We have a little proton A, which is like, I want you, right? It's going to attract the electron. Proton B is like, but I also want you. It's going to attract the proton. You know, C, positive charge C on that side, is going to attract it, right? D is going to attract it. And then E is like, I give up, right? The electron's like, I give up. I'm not going to be attracted to anything anymore, right? And as the electron does that, it means it's not going to experience any force, okay? That means the charge is going to be stationary inside a sphere. Because there's nothing to do, to be honest, guys. You're inside a sphere. It's different when you're outside, right? And you're going to be attracted to the sphere. But if you're inside, the other side attracts you. This other side attracts you. You're like, I give up. Just push me, guys. I'm just going to stick in the middle, right? And that's sort of what's happening in this specific scenario. The charge is distributed, but at the center, in the sphere itself, E is 0. Why am I saying this? Because E is actually the force per unit charge. If you were to put a proton, it's going to be repelled. It's going to experience a force. But inside the sphere, there is no force, guys, because it's stationary inside the sphere. It's not going to move up, down, or to the left. It's just going to remain inside the sphere. And that means E is 0 because there's no force, right? No E, no force. Okay? Pretty cool. So inside the sphere, E is going to be 0 because there is no force experience whatsoever. The electron is confused. The proton is confused. It's like, I don't know where to go. I don't know what to do. Okay, so the radius is going to be inside the sphere. Here it's going to be 2.1, right? Where E is 0 inside the sphere. Calculate the charge on the sphere. Calculate the charge on the sphere. Okay, that's a tricky one. How do they expect me to do that? Remember, I said my relationship? Over here, I said KQ over R squared. But that K actually has a name, right? It's 1 over 4 pi epsilon. So our E is actually going to be equivalent to, right? If we were to think about this, our E is going to be equivalent to Q, like I've said, is Q divided by 4 pi epsilon multiplied by R squared. And I want to find the charge Q. Okay, so what I'm going to do, Q is equals to E multiplied by 4 by pi by epsilon by R squared. Do I know E? Do I know R? I don't. I have a very confusing graph. I don't know what to do. So what I'm going to do is I'm going to go on exactly the surface. If I were to put a little electron exactly on the surface, what is the force is going to experience at that point? The force per unit charge is going to be this little thing over here, right? 1.3 times 10 to the power 5, exactly on the surface of the proton, right? This is so cool, guys. Okay, so we're going to have 1.3, right? 1.30 times 10 to the power 5, right? Times 4 pi. The epsilon is 8.85 times 10 to the power of negative, let me see, times 10 to the power of negative 12. Okay, sorry for that. Multiplied by our radius, which is going to be 0.021, all of that squared, and that's going to give you an E, a charge, 6.4 times 10 to the power of negative 9. Okay, 6.4 times 10 to the power of negative 9. Using the formula for the electric potential due to an isolated point charge, determine the capacitance of the sphere. What is capacitance, right? The capacity to store charge when a potential difference is applied across you, right? You're like, you're a little capacitor. You're going to store some charge. They don't really store charge, but we talk about that. But then capacitance is just Q divided by V, how much charge has been stored per unit potential difference that has been applied. Okay, they said using the formula for electric potential. What formula? If you don't know it, I'm going to slide over here. Okay, if I go over here, I want you guys to look at this, okay? And don't say I never give you anything for free. Don't say Cambridge never give you anything for free in the exam. They give you this, right? The formula for electric potential. Guys, Cambridge has never been nicer. There you go. There's your formula for electric potential. You're going to take a screenshot of that and you're going to, use it, right? Okay. So V, okay, is defined by Cambridge. I didn't define it. Cambridge did, right? As our V is actually our Q divided by, right? So our V is actually Q divided by 4 pi epsilon multiplied by R. In case you're wondering, Keith, I don't want to memorize stuff, right? I don't really want to memorize stuff. Where are you getting this from? Remember, our electric field is the force multiplied by per unit charge. But there's another formula for E. Right? There's another formula for E. If you don't know it, it says that E is actually going to be our V actually divided by our D. If you have a certain voltage that you apply or a certain V that's present across a certain distance, that's going to be the value of V. But you already have E, right? Which was our Q over 4 pi epsilon R squared. But our D at the surface of the sphere, where we have R, the distance we have moved is the radius of R. Right, so at that point is going to multiply by r, and then you're going to have a v of q over 4 pi epsilon r. That's where it comes from. I don't really like memorizing formulas, right? Just have a rough understanding where it comes from, right? I don't ask you to go and say, where did epsilon come from? But I just ask you to have at least an appreciation of where some of these formulas come from. I think it's going to do you more good than harm. Okay, so q is going to be equal to q divided by q over 4 pi epsilon multiplied by r. So our c is going to be equal to 4 pi epsilon multiplied by r. Remember, the q's cancelled out. So if you're left with this formula, it's going to be 4 pi. Our epsilon is 8.85 multiplied by 10 to the power of negative 12. Our radius is 0.021. Punch that all in your calculator. Guys, we have, times have advanced. I wonder how they did this without calculators back in the day. Okay, 10 to the power of negative 12 Faraday, right? In the honor of Faraday. That's our capacitance. Okay. The next topic, the op-amp. We don't really do that. We don't really do this in our syllabus, so we're not going to cover it. If you're curious learner, I really encourage you to read it. Fun topic. But I've forgotten some of the stuff, to be honest. But it's a very, very fun topic to do. Question 8. Two straight wires P and Q are parallel to each other, as shown. There's a current in each of the wire in the direction. The pattern of the magnetic field in the normal wire due to the current is also shown. And that's true, right? Current moving in a wire creates a magnetic field. If you didn't know, right? If current is moving, it's going to generate a magnetic field. Guys, to be honest, I don't know why that's true, right? I've always asked why. Why is it that current exerts a magnetic field? But apparently it's a fact. And if you really want to know, we can delve deeper into that. A lot of complicated physics, but it's very fun. Understanding why is it current is able to create a magnetic field, that's going to be very interesting. So we have wire P, and we have a plane, right? And we have a magnetic field pattern that is produced. And what we want to do is sort of draw arrows of the magnetic field lines around wire P to show the direction of the field. So we're going to use our hands, right? We have Fleming's left-hand rule, Fleming's right-hand rule, the right-hand grip rule. How do you know which one to use? I don't know, right? Just, figure out and know in what scenario you're going to use what hand. So in this case, we're going to use what we call the right hand grip rule, right? The right R, hand H, grip G, rule R. The RGP, the right hand grip rule, right? So we want to draw arrows on the magnetic field lines around wire P to show the direction of the field. Okay, so you're going to put your thumb up, right? That's going to show the direction of the current, okay? Then you're going to wrap your hands around. And as your hands are moving, you're going to sort of point them like funny, right? And as you're doing that, you're going to show yourself the direction. So if you try it, please do try it, guys. I'm not going to see if you did it, but do it at least, right? So you're going to have something like this. And on this specific side, you're going to have something like this, right? And what you're just going to see on the syllabus, on the marking scheme to be more specific, is you just need an anti-clockwise arrow, right? An arrow that is moving anti-clockwise. And we use the right hand to sort of describe that. Okay. Determine the direction of the force on wire Q, okay, due to the magnetic field from wire P. So what you're going to realize is that if you have two currents that are moving in the same direction, they're going to sort of attract each other. If you have two currents moving in opposite directions, they're going to repel. Sort of opposes everything. I always expected like charges like charges repel and like charges attract. But with currents, they attract, and like currents, they repel. Okay, so I want to determine the direction of the force on wire Q due to the magnetic field from wire P. Now, I can't put my hand on the screen. I wish I could. Bit tricky. But what you're going to use is called a Fleming's left-hand rule. Okay, so how are you going to do it? The thumb stands for the force, right? So I like to call it FBI, right? So F is for the force, B is for the magnetic field, and then I is for the current. But when I was taught sometime later ago, there was this teacher who liked Manchester Football Club, so it was like Manchester Football Club. Manchester, it was like motion, right? Motion. and then F is field, and then F is current. I was like, just find something that starts with F and say force, field, current. But Manchester Football Club, you can use that. Motion, field, then current, or FBI, force, field, B, and then I is the current. Okay, so if you're using it there, our B is acting like this, right? Like in that direction inwards. Okay, then our current, you're gonna point your thumb up, you're gonna point your finger up, right? Your current is up. That means your force is going to be to the side. Okay, so your force is going to be to the side, like so. Right, that's sort of how we do it. So we just have to state it in words. We've been asked to determine the direction of the force on wire Q. We can just say force is to the left. Okay, force is to the left. Force is to the left. Okay, that's doable, right? Force is to the left. And then, as a result, wire P is going to react, right? If you pull me, I'm going to pull you, right? That's what it happens. So they're going to attract each other with the same force. It doesn't matter what current you have. You're going to attract each other with the same force. Physics is weird at times, but it's Newton's laws of motion, right? If you're going to push a book, the book is going to push you back, and the book is not going to move. If you're going to punch a wall, the wall is going to punch back. But it really doesn't matter how much mass something has. If you're going to punch it, if it's capable of returning it, it's going to do it. The same with currents, right? Regardless of the current, because of Newton's third law, if it's going to push me, I'm going to push it. So if Q is going to pull here, wire P is also going to experience the same force, equal magnitude, but opposite in direction. That's going to be our answer to the part 3. The current in wire Q is less than the current in wire P. State and explain whether the magnitude of the force on wire P is less than, equal to, or greater than the magnitude of the force on wire Q. It doesn't matter what the current is, because of Newton's laws of motion. Third law of motion, the force is going to be the same. So we're just going to mention that the force is the same. And why is it the same, guys? Because of this guy said so, right? Because Newton said so. Because of Newton's third law. I didn't say so, right? I wish it was Keith's third law, but who's counting? Newton's third law, right, of motion. Okay, that's pretty decent. I know this is a little bit absurd. Some of you might not believe me, but guys, I want you to think of this. You have two magnets, right? Magnet A, magnet B. The magnets, even though they're of different sizes, even if they're going to repel each other with the same force. If you put them over here, they're going to repel each other with the same force. What's different might be how much one magnet moves, but it's going to be the same force, guys. If you have two masses, a big planet and a small planet, the star and the moon, they're going to give the Earth and the moon, they're going to exert the same gravitational force, but they have different masses, right? How is that even possible? They have different masses, but Newton told us if a force occurs, there's going to be a reaction to that action, and that reaction is going to be equal to the action, regardless of the circumstances around it. This question could have been phrased and asked: the mass of body A is less than the mass of body B. Explain if the magnitude of the force between them is equal. You're going to say it's equal. If body A exerts a force on body B is going to exert an equal but opposite force on body A. Okay, this is NMR, not really in our syllabus anymore. We're not going to talk about that. If you're very interested, go and research, guys. Very, very interesting topic. Okay, number 9, define magnetic flux linkage. How do you define magnetic flux linkage? Well, if you're using a formula, this is Bahn, right? This is Bahn, but basically it's the magnetic flux density, okay? Magnetic flux density multiplied by the area, okay? Multiplied by the number of turns, okay, where the area is perpendicular to magnetic field. I know it can be a little bit abstract to just sort of cram that and memorize it, but I want you to think of flux. I'm going to explain a little bit about what this whole flux situation is, right? Magnetic flux is the flow of magnetic field lines. Flux is related to the flow of things across a certain area, or just the flow of things in general. So if magnetic lines are entering a specific area, that's flux. If magnetic lines flowing into an area, so if you have magnetic lines like so, just flowing into a specific area A, right? Those magnetic lines are going to sort of create a magnetic flux, the flow of this bundle of this bundle of magnetic field lines is going to be flask, right? But you have a specific area here that measures the density of that flask. How dense is it? It's sort of related to how many magnetic field lines have flowed through a specific area. That's our density, right? The flask divided by our area. How many of those have flowed across a specific area? That's magnetic flask. Okay, but then with the flask linkage, you want to link different coils together, and they gave us a little coil over here, right? These coils together, you need the number of turns on the coil. Now you're linking different areas. You had one area over here. Now you have another coil with another area, another coil with another area, and you want to find the magnetic flask that's linking, how all of those are linked together. And you're going to multiply by the number of turns. That's why we have BAN. B stands for magnetic flask density. A stands for the area, and N stands for the number of turns. Okay, let's move on. A solenoid of diameter, that's a solenoid, 6 centimeters and 540 turns, is placed in a uniform magnetic field as shown. The variation with time of the magnetic flux density is shown in that figure. Calculate the maximum amount of induced EMF in the solenoid. What we're going to use is what is known as it's a little bit tricky to wrap your head around it, but it's Faraday's law, microfaraday. The induced EMF is equal to the rate of change of magnetic flux linkage, okay, or the rate of change of magnetic flux. So it's going to be delta B multiplied by A multiplied by N divided by delta T. So in other words, you can sort of see delta T over delta A over here. We have delta B over delta T, that's sort of here. And looking at this graph, your flux density B over here, you have time over there. You can sort of tell that the EMF somehow is related to the gradient, right? The gradient, these specific quantities are sort of related to the gradient to some extent, okay? And where you're going to have the greatest EMF, and why am I concerned about the greatest EMF? Because I've been told the maximum magnitude is where you're going to have the greatest gradient, right? Very steeper gradient means a greater change or a greater EMF is going to be induced. So in this specific scenario, we want to find that specific time. In this case, it's going to be here, where we had the greatest change in magnetic flux, and that's going to then translate to a big change in the EMF that's going to be produced. So the change in B is simply just 250 and milli Teslas, not that kind of Tesla, guys, just it's a unit. So it's 0.250 multiplied by our area. Our area we've been given, right? Area is pi r squared. The radius is 0.030, and then all of that squared multiplied by, how many tens do we have? 540 tens divided by our delta T, our change in our time. Here we have 1 second, 1.2 seconds. You punch that in your little calculator, you're going to get 0.32 volts. So our EMF, 0.32 volts. Very important for you guys to be thinking of that. Okay. A thin copper sheet X is supported on a rigid rod so that it hangs between the poles of a magnet as shown. We have a magnet, and then it's starting to oscillate back and forth, back and forth, back and forth. Sheet X is displaced to one side and then released so that it oscillates. Okay. A motion sensor is used to record the displacement of X. A second thin copper sheet replaces sheet X. Sheet Y is the overall dimensions as X, but is cut into a shape like so. So it's cut into multiple shapes like so. The motion again is used to record the displacement. The graph in Fig 9.5 shows the variation with time t of the displacement X of each copper sheet. Two graphs that have been produced. So the name of the phenomenon illustrated by the gradual reduction in the amplitude of the dashed line. And remember, what's important here is the word gradual reduction. Gradual reduction, that's linked to damping, right? Damping, the reduction in the energy of a wave, or it can be of a system that's oscillating. So in this specific case, the gradual reduction in the amplitude of the dashed line is just going to be damping. Not just any damping, light damping, right? A little light damping here and there, right? Doesn't hurt anyone, right? damping occurs. It can be swinging on a swing, and then you come to a halt. That's damping that has occurred, right? And that's sort of the phenomenon that we're sort of trying to illustrate here. Okay, moving on to the next question. We've been asked to deduce which copper sheet is represented by the dashed line. Explain your answer using the principles of electromagnetic induction. Pretty tricky, but let's try it. Okay, which copper sheet is represented by the dashed line? Okay, so, right, so our sheets, they cut the magnetic flask, right? Our sheets cut the magnetic flask, and as that is occurring, it's going to cause an induced EMF, okay? It's going to cause an induced EMF. It's going to cut, causing an induced EMF. And then what you're going to see is that the induced EMF on its own, okay, the induced EMF is going to cause, so the induced EMF causes currents, right, in the sheet. Because an induced EMF, if there's an EMF that is now present in that sheet, it's going to cause a current, to be present, right? So induced EMF causes current in sheets. Okay, it causes currents in sheets. Right, so there's one aspect that we're still going over here. But then the current in the sheet is going to dissipate energy, right? The current in the sheet is going to dissipate energy. If you have a phone, right, if you touch the socket as you plug it in on the adapter, you're going to figure out that it's going to be hot, right? Current is dissipating energy, right? An element, current dissipates energy. So current is going to dissipate energy. But you can't just make energy from nowhere, right? Where is this energy that the current is dissipating? It's taking some of the energy from the amplitude of the oscillations, right? It's going to take some of that energy and use it to sort of create this thermal energy, dissipate that energy. So that means the amplitude is going to decrease, right? Hence, the amplitude is going to decrease as a result. And the amplitude is decreasing. Why? Because the current is dissipating energy. So losing energy, meaning that the amplitude itself is going to decrease, like a child, right? If the child is sort of swinging and swinging, it dies because the child is overcoming frictional forces. So they're dissipating energy to do that. And in this case, we're dampening it because the current is dissipating energy in overcoming that sort of dampness that's occurring. But if you look at these guys, let's look at this, right? Without even looking at much, right? Which one is going to have a greater current, X or Y? Y is cut up. So electrons are not going to be able to jump from here to here, right? The electrons are just going to be circulating here. But then if you're looking at this specific scenario, everywhere all the electrons are going to be moving. You can literally tell that from this one, the majority of the electrons have been removed, right? There's a strip that was taken away, multiple strips that were taken away. So that's going to affect the number of electrons, and the current that will be present in that sheet is going to be different, right? And because of that, it means that, and like I've said, you have a smaller surface area, fewer electrons are present. They can't just jump over there. So that means the current present in sheet Y is going to be smaller, right? So smaller, current, okay, in sheet Y, right? Smaller current in sheet Y, or you could say larger current in X. Really doesn't matter. Larger current in X. And then that means if you have a larger current, guess what, right? A larger current means a larger dissipation of energy, right? A larger current means you're dissipating a lot of energy, right? Means more dissipation. A smaller current means very little dissipation. So you're still going to oscillate pretty fine. But if you have a larger current, you're going to dissipate a lot of energy, right? Dissipates more energy. So our dashed line can only be X, right? You can go about this using Lenz's law again as an alternative. Talk about how current causes a resistive force, and that resistive force opposes the induced EMF that produced it. Sort of use your hands to figure out the EMF is induced, but it's a bit tricky to grasp your head around it. But I like the energy one more, right? Currents has to dissipate energy as it moves, because electrons have to overcome resistance. They dissipate energy. They have to get it from somewhere. They get it from the oscillation itself, the kinetic energy that's occurring here. And the smaller current you have, the smaller that dissipation. The larger the current that you have, the greater the dissipation. So more dissipation in X. So the dashed line that's going to dampen is going to be X, because more of the energy is being lost, right? So it's going to dampen. It's going to have a gradual reduction in the amplitude, a gradual reduction in the amount of energy. For question number 10, we're almost done. The output potential difference of an alternating power source, represented by that. Calculate the root mean square RMS PD of the power supply. VRMS, according to your syllabus, is defined as V divided by R2. What you need is the peak power, peak potential. In this case, what you need is the peak potential, 320 divided by root 2. And if you divide 320, okay, divided by root 2, what you're going to end up with is 230 volts. So you're going to have 230 volts. Okay, we want to determine the period T of the output that is there. We know that omega is 2 pi divided by T, right? So our T is going to be 2 pi divided by our omega, which is 100 pi. And that's going to give you 0.020 seconds, 0.020 seconds, okay? Part C, the power supply is connected to a resistor R and a diode that is given. So the name of the type of rectification that is produced by the diode that you have been shown. We have two kinds of rectification. The point of rectification is that we have AC current and we're trying to restrict it so that it becomes DC current. Sort of trying to convert it, right? And we have full wave rectification and half wave rectification. For full wave rectification, you're going to need a full bridge rectifier. You have 4 diodes, that kind of scenario. But then with the half wave rectification like that, you're going to have one little diode that's just going to restrict current, right? So as current moves in this direction, it's going to open its gates. We allow you to enter through, right? Current flows in. But as current tries to oppose, it's going to block and say, no, you can't come back, just go, right? So it means that it's only now going to be in one direction only, sort of, in some sense. In other senses, it won't be coming back, but we can take it, right? So we can basically say the name of the rectification is half wave rectification. Okay, let's move on. On Fig 10.2, sketch the variation with time t of the PDVR across R from time t is equals to 0 to time t is equals to 40 milliseconds. 40 milliseconds, that's 0.04. Okay, that's 0.04. Sorry, 0.040 milliseconds. Sorry, just 0.04 seconds, right? 40 milliseconds is 0.040 seconds. We have a period of 0.02 seconds, right? So it means that from 0 to 0.2, that's going to be a full period, right? So remember our peak is 320, right? So we have 0, 20, 40, 60, 80, 100. So 320 is going to be here. That's going to be our peak here. So we're going to start here, right? And then we're going to start with a full wave like so. We go up and then we reach down. Sorry. It's a bit tricky to draw a wave on this specific computer. I mean, it's always tough. I think you guys would do it much better than me here. Okay. We have this kind of scenario over here. Now we are trying to go in the opposite direction, but the half the diode will be like, no, you can't go back, right? So for that whole time we were supposed to be down, it's going to be 0. Nothing will be conducted for that specific point. Then we go to the positive. It's like, okay, you can pass through, right? We give a peak like so. Make sure it reaches 320, guys. Then when it's here, it's like, no, you can't. Then it's a straight line. So you're going to have this little hump, right? That's for half wave rectification. Move in one direction. You're going to have a positive, no direction, 0, positive, and then 0. On Fig 10.1, draw the symbol of a component that can be connected to produce smoothing of a VR, right? Smoothing, what is smoothing? You're sort of trying to reduce the effect of these gaps that are over here. There's no energy here, guys. So you can use sort of what is called a capacitor. It stores some of the energy so that when you have nothing, right, you're going to have that sort of hump. Like for example, in COVID, if you stored some food, right, when, there wasn't, or for example, there was lockdown, right, where we were. So you'd go out and buy some food and then stock it. When there's a lockdown, you'll be fine. You have to be eating that food throughout that whole entire time. That's the same thing that's happening here, right? You're going to put a capacitor and you're going to connect it like so in parallel. Okay, like this, right? This is going to be a capacitor that you're going to put there. We're just putting a symbol of a capacitor added in parallel, right? But a capacitor really just has 2 parallel beams, like so. They're of the same line length, right? So that when this thing no longer conducts, the capacitor is going to be like, I'll provide you, right? And then like goes like this, then it starts providing things to this here. So this is our capacitor, 2 parallel lines, like so, and it's going to be your capacitor. It sort of stores excess charge so that when you need it, it gives it. Move on to the next question. Electrons are accelerated through a potential difference of 15 kilovolts. The electrons collide with a metal target, and a spectrum of X-rays is produced. Okay. If you wonder why they're called X-rays, right? The guy who discovered them didn't know what to call them, so he was just like X-rays, right? X for a known variable. Physics is crazy at times, but we sort of want to describe how X-rays are produced. And in this case, you want to describe a continuous spectrum of energies of X-rays that is produced. So if you look at the graph for X-ray production, if you look at over there, it's going to have the continuous distribution over there. We call it the Bremsstrahlung distribution, right? Then you're going to have some sharp peaks. The sharp peaks will be for another video, right? In this video, we're going to talk about the continuous spectrum that you're seeing over there. And we're going to explain the shape in a little bit, but I just want you to bear with me over here. With X-ray production, we have electrons that are moving at a very, very fast speed, right? Electrons are moving at a fast speed. Then they hit the metal target. They're going to hit nucleons, they're going to hit protons, they're going to hit electrons, and they're going to be decelerated, right? So electrons decelerate. Okay? Electrons decelerate on hitting the metal target. Okay, they're going to decelerate when they hit the metal target, so X-ray photons are produced. Okay, so X-ray photons are produced, right? Okay. But there's a range of decelerations. It's not like they're all going to decelerate to the same extent, right? Some is going to decelerate a little bit, some is going to decelerate a little bit, some is going to decelerate a little bit, as to all be hitting the protons. They're decelerating to different extents, right? So there's going to be a range of decelerations that is going to exist, because they can't all just decelerate to the same extent, right? And then the photon energy itself depends on the level of magnitude of deceleration. So we're now going to have a spectrum of energies, because the photon energy actually depends on the magnitude. If you stop, all that kinetic energy is being compressed and packed. If you're wondering what a photon is, it's just a packet, a quantum of electromagnetic energy. So all the kinetic energy is sort of being packed and creating little photons that are going to be then emitted. So it depends on magnitude of deceleration. Okay, on magnitude of deceleration, right? And if, in case you're wondering why is the shape like that, it's a normal distribution curve, guys, because it's probability. In an exam, you're going to write a test, very few people pass, very few people fail, the rest are in the middle. The same with here. You're going to have electrons on a range of energies, starting with an initial wavelength, because the wavelength corresponds to initial energy produced. And it's going to form a spectrum, a continuous variation, that is, because you're going to have very few that are going to have very high energies. This is high energy because you have a very small lambda naught. And you're going to have very few X-rays that are going to have very low energy, because they're going to have a longer wavelength existing on that graph, because that graph compares the intensity versus the wavelength, right? So the intensity is the number times, so intensity itself is defined as the number times h times f divided by the time times the area, right? Because power over area, power is energy over time. That's where we get this specific formula. So our intensity is dependent on the number. And because you're very small at extremes, you're going to have a very low intensity at extremes, right? But not necessarily zero, but you're going to have a low intensity. But then the rest is going to be in the middle. You're going to have a high probability of having electrons arriving in the middle. That's why you have a peak that is like that, a continuous spectrum. But then why is it continuous? All you just need to know, electrons decelerate on hitting metal target. There's a range of deceleration, and then the photon energy depends on the magnitude of radiation. If you like to cram, I just call it DRM, right? Deceleration, electrons decelerate. There is electron decelerate. There is a range of deceleration, and then the magnitude of deceleration affects the photons, right? DRM, dream, right? Sort of a little acronym that I just used to remember that, right? D for decelerate, electrons decelerate, R for range of decelerations, and M for the magnitude of the accelerations. Calculate the wavelength of the highest energy X-ray photon produced. So this occurs when the electrons comes to an immediate halt, right? So if you're accelerating through a potential difference of 15 kilovolts, what's going to happen is that the electron is going to have an energy which will be EV, right? Because work done is going to be the charge multiplied by the potential difference. Because potential difference is the work done per unit charge. You got it? So in order for you to have the highest X-ray photon produced, you're going to give all of your energy to that photon. So EV is going to be equivalent to hc divided by lambda, because all of the energy from the electron is going to go to the photon itself, right? All of the energy is now going to go to the photon. So what you want to find is the value of lambda. So the value of lambda is just going to be hc divided by E multiplied by V. The value of H, 6.63 times 10 to the power of negative 34. The value of C, 3.0 times 10 to the power of 8, divided by the value of E, 1.6 times 10 to the power of negative 19. The value of the V, remember 15 kilovolts, 15,000. That's going to give you a lambda that will be of magnitude, right? That's going to give you a lambda of magnitude 8.3 times 10 to the power of negative 11. Remember, all of the energy is now going to the photon itself as a whole. So you're going to have 8.3 times 10 to the power of negative 11. Over to the next graph. A beam of X-rays has an intensity I0. The beam is directed into some body tissue. After passing through a thickness X, the intensity is I. So passing through some body tissue, the intensity is I. After passing through a thickness X of the tissue, the intensity is I. The graph below shows the variation of X with ln I over I0 R. Remember, I is actually I0 e to the power of negative mu by X. Right, so it means that I over I0 will be equal to e to the power of negative mu multiplied by x. So it means that ln of I divided by I0 will be equal to, you introduce ln on the other side, you're going to have negative mu divided by x. So it means a graph of this against this is going to have a gradient. Okay, it's going to have a gradient of negative mu. So it's going to have a gradient of negative mu, right? And I've said this because I have an equation. I introduce lns on both sides, right? And then I have y is equals to mx. So the gradient is going to be negative mu. So I've been asked to determine the linear attenuation coefficient mu for this X-ray beam. So it means that mu is just going to be negative the gradient, right? That is going to be the value of my mu. Okay, if I want to find my gradient, it's just comparing two values. I take a point that I want here on that specific graph, right? So I'm going to have two, if I look here, over here, I'm going to have, let's say I take this specific point, that's 10, right? And then if I take here, that's 2.4, that's 2.08, right? 2.04, 2.08. I take this point, I have 10 over there, I have 2.08. You can take any point you want. Just make sure you're consistent. You can take 6 and take 1.26. right? Sorry, 1.24, right? Which would be, you can take 6, then you can take 1.24. Just make sure you take a point that is consistent. But essentially, so I hope you understand, guys, where we got the mu. Like I've said, your mu is the negative of the gradient that will be present, right? So to get your gradient, it's just going to be 2.08 divided by 10.0. Take any value you want, guys. You can get the same answer, basically 0.21. Okay, a recap. Like I said, we know this is the equation for attenuation, right? The intensity that you have is equal to I0 e to the power of negative mu x. This equation describes decay, and if you put I over I0, introduce ln on both sides, it will help you find the gradient, which would be negative mu, and then ln I over I0 is going to be equal to negative mu x, right? You have y, you have x. The gradient is going to be negative mu, right? So in this case, our gradient is negative mu. So mu is going to be negative of our gradient, but our gradient is a negative value. Guys, it is a negative value because of these negative over there. So negative of a negative, right? Change in x, in y, over change in x, 2.08 over 10.0. That's going to give you 0.21, which is going to be the value of mu that's going to appear over there. Right. Now I want to determine the thickness of the tissue that the X-ray beam must pass through so that the intensity of the beam is reduced to 5.0 of its initial value. Remember, we said ln of I over I0 is going to be equal to negative mu multiplied by x. Now I want to find the value of x so that the beam is reduced to 5% of its initial value. So if you had I, okay, for it to reduce to 5% of its initial value is going to be 5% of its initial value, right? That's going to be the result that you're going to get divided by the initial value, which is I naught. Our ln of that's going to be negative mu multiplied by x, right? These two cancel out, so you have ln 0.05 being equal to negative mu divided by x. But why did they ask you to find negative mu, guys? So that you can be able to find x. You guessed it. So x is going to be ln 0.05 divided by negative 0.21. That's going to give you a value of x of 14 centimeters, right? Very important. So x-rays are pretty cool. I'm working on a playlist for these kind of topics, medical physics. Tell me if you like it, so that I can sort of speed up the process. But basically the whole process of x-rays is that you have an x-ray tube that sort of produces these x-rays, right? You want to accelerate electrons in that tube, and by accelerating electrons, they're going to bombard the metal target. And as they do that, they're going to cause a range of decelerations to occur. Then that range of decelerations that is present is going to sort of affect everything that's going to occur, right? The range of decelerations means that the energy is going to be packed and given to the photon, and the photon that the energy that the photon gets depends on the magnitude of the deceleration. So those are the key points, guys. Electron decelerates, hitting the metal targets, DRM, don't forget, right? Decelerate, range of accelerations, magnitude is affected. And if you want to find the wavelength, all of it is given to the electron. Work done per unit charge is V. So V is charge times EV, and that helps you find this specific thing, hc over lambda. Okay, and then this helped us find our graph. We looked at our graph over here. We give a little graph like this. We were supposed to know the attenuation coefficient. Then that helped you find this specific relationship. Okay, moving on to the last question. We are almost done. Okay, radioactive decay, another fun topic where we talk of materials that can decay. We have a lot of materials really that can decay, but with uranium, we have a lot of places where nuclear physics has popped up. The Hiroshima and Nagasaki event, probably triggered by radioactivity and the research in radioactivity and the decay, radioactive decay. So we just want to understand what happens when we have radioactive decay. So first, we have what we call spontaneous, right? Spontaneous means for decay to be spontaneous, it means it is not affected by external factors. Okay, it is not affected by external factors. Someone can say your grade is not affected by external factors, right? Meaning no teacher, no amount of book, no amount of studying is going to change it. Pretty brutal, but might be true, right? And it's going to hurt, but basically it means you cannot be affected by external changes. That's what we call spontaneous. And for random, well, random actually means cannot be predicted. You can't tell. And that's very sad. You can't tell. You have multiple nuclei in a sample. You can't tell when one nuclei is going to decay, which nuclei is going to decay, how many nuclei are going to decay here, here, and there. You really can't tell. So what you can't do is you can't predict. Okay, you cannot predict when, right, a particular nucleus decays. When a particular nucleus, okay, decays. Right? A fancy one might say you cannot predict which nucleus can decay. So you can have multiple nuclei, you can't predict which nucleus will decay, or you can have one nucleus and you cannot predict when it will decay. So in this case, you can't predict which nucleus will decay, or you can't predict when each nucleus will decay. Okay, and then moving on to part B, we have strontium-90. So this is strontium-90, which is an unstable nuclide. The activity of a sample of 1.0 times 10 to the power of negative 9 kgs of strontium, 90 is 5.2 millibecquerels. Becquerel is sort of a measure of activity, and we want to determine the decay constant lambda of strontium-90, right? We have a relationship that relates these specific things. Why? Because the activity, dN over dt, is directly proportional to the number of particles. If you have a larger sample size, you're going to have a greater decay. If you have a smaller sample size, you're going to have a smaller decay. So dN over dt is related to the number of particles. And we can say this is the A is probably a negative lambda that shows us that it's a decrease, but we just call it A is equal to lambda n, right? Because the decay itself, if you have a lot of particles, they're going to decay a lot, right? The decay itself is related to the number of particles. A lot of particles, a greater activity. Smaller particles, a smaller activity. So we have this equation, A is equal to lambda times n. If you want to find lambda, it's going to be equivalent to your activity divided by the number of particles that you're going to have. But if you want to find the number of atoms, what you're going to do is that, well, if you think about it, the number of atoms, we have the mass, right? We can find the number of moles, which is equal to the mass divided by mr, right? Our mass being 1.0 times 10 to the power of -9. That's our mass, right? Then our mr, if we divide by this, we're going to have 90, right? 90 being our mr, right? So if we do this, 1.09 times 10 to the power of -9 divided by 90, you're going to get the number of moles, right? Which will be present over there. But I want you guys to think of something. Whenever we define number of moles, we have our mass in grams. If you've done chemistry, it's going to be a little bit much easier. If you haven't, it's going to be tricky, but you're going to get it eventually. But then essentially what I'm talking about is that we're usually given our mass in actually grams. So if you look at the booklet, the mr is usually the grams per mole. So this is actually 90 grams per mole. So you need to convert this to kilos, and you're going to multiply by 10 to the power of -3 from grams to kilos. So this is going to be your number of moles. And if you want to find the particles, number of moles will be equal to number of particles divided by Avogadro, 6.02 times 10 to the power of 23. Okay? If you want to find the number of particles, is going to be the number of moles times 6.02 times 10 to the power of 23. Okay, so the number of particles n is going to be equivalent to, so n is going to be equivalent to the number of moles, 1.0, 10 to the power of -9. And remember, it's 90 times 10 to the power of -3, not just 90, because it's grams per mole, multiplied by 6.02 times 10 to the power of 23. That's going to give you a value of n, which is going to be 6.693, okay, 6.693 times 10 to the power of 15. Then our activity is 5.2 times 10 to the power of 6 becquerels. That's going to give you a lambda, which is 7.8 times 10 to the power of -10. You have 7.8 times 10 to the power of -10. That's going to be your value of lambda. Multiple ideas thrown around, but on this side, the main focus here is just finding the number of moles on this side so that we can be able to find the number of particles that are present. And on this side is the relationship between activity and the decay constant, lambda. And on this side, we're making lambda the subject of the formulae, right? Using this specific equation and making lambda the subject of the formulae. And then this is sort of helping us to then compute everything up after we have done so. Multiple ideas, one idea over there, one idea over there. But the overall goal of all these ideas is so that we can be able to just find the value of lambda. The last question, we're given the activity of the sample after a time of 1 half-lives, and it's found to be greater than the expected 2.6. So you were expecting something and it doesn't materialize. Happens in people's lives, very sad. But then you were expecting to get 2.6, but what you're finding is that it's greater. Isn't that weird? And activity refers to the decays that are occurring per unit time. How many decays, the rate of decay per unit time. And you're finding out that it's greater. The actual activity is greater than the expected 2.6. What could be a cause? Well, after decay, you're going to produce what is called a daughter. Parent, daughter. Parent nucleus, daughter nucleus, right? And if that decay, if the daughter is radioactive, it's also going to cause activity. Right? And activity is just radiation, how much has been emitted, right? And you can't really tell, is it the daughter that produces the radiation? Is it this or this? You can't tell. But we want to measure the decays. So the daughter can be radioactive, and that can cause decay, right? So, you have an unstable parent, probably going to produce an unstable daughter. It could happen. I'm just saying. Daughter nucleus is unstable and so can undergo decay. Okay, so just sort of be thinking of that. Can undergo decay. So be thinking of those multiple ideas. A lot of ideas around, but then try to sort of see how they can be connected. We're sort of done with the whole paper. A2 paper is pretty long, But then if you have a grasp of the ideas, you can see a little bit of each concept comes along. And if you understand, have an overall understanding of the whole concept, you should be fine. So I really encourage that you read a lot for A2 so that you have a lot of understanding and you're able to piece everything together. And conceptual understanding, guys. This paper is long and you need to understand every single thing in detail. Do read in great detail. Thank you guys for watching, and I really hope that this was helpful. Please do like and subscribe, and I'll see you guys in the next one.